Hello, in this video I will explain the application of Fourier transform in real life. Fourier transform methods are most heavily used in the analysis of signals and systems. Fourier transform can convert non-periodic continuous signal in time domain to continuous signal in frequency domain. One of the application of Fourier transform is the filter. So what I can see is filter is a system which is designed to limit the spectrum of the signal to pre-assign the frequencies. Usually, filter consists of low pass filter, band pass filter, high pass filter, and band stop filters. These filters are commonly used to remove the unwanted spectral content from a signal. So later I will show you the differences between these four filters. So firstly I will explain the low pass filter, which is, you can see this is the code for the low pass filter, and I'm gonna run it. So this is basically the graph that will appear. This is the input and output spectra of low pass filter, and you can see this is the input spectrum and this is the output spectrum for the low pass filter. So what you can see is low pass filter, you will remove the high frequency content and you will pass the lower frequency signal. So you can see this is the high frequency. It will remove in low pass filter, so it's gonna be like this, and the lower frequency it will bring to the result of the low pass filter. So this basically this is the output of the low pass filter, which is the high frequency will be removed out. So this is the time plots of input and output low pass. You can see this is the input signal and this is the output of the low pass filter. Low pass filter basically used to remove noise and provide smoother form of signals. And you can see the form of this output of low pass filter is quite uniform and have a smoother form of signals. So this is the impulse response of the low pass, its amplitude, and this is the frequency response low pass, which is this is the magnitude and the phase. So in conclusion, for the low pass filter, pass the signals with frequency lower than a certain cut-off frequency. Actually, what I'm filter here is an audio file, which you can see this is the filter to input of audio file. So I will play the original audio for the this is the original audio. And this is the audio after the low pass filter. So you can hear, right, the higher frequency of the original audio have been cut off, and after the low pass filter, the audio only play the lower frequency of the signal, and which is the base of the song. So now I will play the code, I will run the code for high pass filter, which is another types of filter, and this is the code. This one, the code for high pass filter. So I'm going to run it. Yeah. Okay, this is the input and output spectrum for high pass filter. You can see this is the input spectrum and this is the output spectrum. Basically, the high pass filter will take the higher frequency of the spectrum, and we will cut the lower frequency. And you can see this is the this is the low frequency of the spectrum, and when it passes to the high pass filter, it will be cut off like this. And the high frequency here will be taken to the input, to the output of the high pass filter. And this is the time plots of input and output high pass, which is you can see here the filter signal of high pass is quite not uniform because it takes the high frequency, right? So it's basically not uniform. So this is the impulse response of high pass, and here this is the low frequency that we cut off, and this is the amplitude of higher frequency that we taken to the after the high pass filter. This is the frequency response of high pass, the shape here, and the phase of after the high pass filter. Okay, high pass filter have many use, such as blocking DC from circuitry sensitive to non-zero average voltage or radio frequency device. They can also be used in conjunction with a low pass filter to produce a band pass filter. So from what we can compare to the low pass filter earlier, the high pass filter is the opposite to the low pass filter, which is the high pass will take the high frequency of the original spectrum, original signal. So now I'm gonna play to you the original audio. Okay, and after the high pass filter, so you can differentiate, right, whether the difference between the original audio with the high pass audio. The audio will play only the high frequency of the original audio. Okay. So now I will show you the band pass filter. The other types of filter that I will show you is the band pass filter. So this is the coding for band pass filter. You can show, and I will run it. Okay. So this is the input and output spectrum of band pass filter. This is the input and this is the output. Okay, basically a band pass filter is a device that passes frequencies within a certain range and reject the frequencies outside the range. From this graph, from this visual, you can see this is the range after the band pass filter that is taken. So what I can see is maybe it's from the 0.25 to 0.75 range frequency that is filtered from the band pass filter. So band pass filter also widely used to are widely used in a wireless transmitter and receiver. So the main function of such a filter in the transmitter is to limit the bandwidth of the output signal to the band allocated for the transmission. So this is the time plot of input and output bandpass, which you can see this is the input signal, and after the bandpass filter, the signal will be like this. Basically the time plot is the input signal against the times. Okay, this is the impulse response of bandpass filter, and this is what I told before, which is after the filter, the value of frequency at the certain range only that will be taken. So let's say the sample is 10 to 35. So the frequency at this range will be taken after the filter, and the rest of the frequency will be cut off. Okay, this is the frequency response of bandpass, the magnitude here, and the phase of the bandpass filter. So now I'm gonna play you the audio before and after the bandpass. Okay, that's before, and this is after bandpass. Okay, you can see, if you notice, the bandpass filter allows signals within a selected range of frequency to be heard or recorded, while preventing signal at unwanted frequency from getting through. Okay, in conclusion, what I can conclude from this bandpass filter is the unwanted frequency will not be filtered, will be through the bandpass filter, which as the result of the output of the bandpass filter, only the selected frequency will be passed through the filter. And also a bandpass filter also optimizes the signal to noise ratio and sensitivity of a receiver. Okay, now lastly I will show the band stop filter. Before that, this is the time plots of input and output band stop, and as you can see, this is the input signal, and when it's through the band stop filter, the signal will be something like this, which is quite uniform. And this is the impulse response of the band stop. You can see this is the amplitude here, and yeah, this is the frequency response of band stop, the magnitude here, and the phase will be coming something like this. Okay, so what I can tell you about band stop filter is band stop filter has two pass bands and one stop band. The characteristics of the filters are exactly opposite to the band pass filter, which you can will be clear like this. This is the band stop filter, and this is the band pass filter, which is the result is opposite, right? So a band stop filter, also called the band rejection filter and band elimination filter, it uses a high pass filter and a low pass filter connected in parallel. So band stop filter use the high pass filter and low pass filter, which is connected in parallel. The low frequencies are given to the low pass, whereas the high frequency are given to the high pass filter. So one of the application of the band stop filter in audio is the band stop filter used in high quality audio application like PA system. You know, PA system, usually the PA system use this type of filter to make the sound better. Okay, so now you can see the difference between low pass and high pass filter, band pass and band stop filter, which is low pass filter and high pass filters are opposite to each other. Low pass filter will take the lower frequency, while the high pass filter will take the high frequency of the signal. And the band pass will take the frequency within a certain range, while the band stop filter will take out the frequency of the certain range. So how do I relate this filter to the Fourier transform? So as you know, the Fourier transform convert non-periodic continuous signal in time domain to continuous signal in frequency domain. So if you look at the original formula of the Fourier transform, which is we use the fj omega fde and negative to the power of negative j omega t dt. So this omega is equal to 2 pi f, which is the f we use to have this frequency. This frequency we use to filter, to filter the signal. So this this is the harmonic, the input harmonic. This is the input signal, which is the harmonic. Harmonic is made out of many sum waves with different frequency. And as we learned before, Fourier series will make this harmonic, whereas the Fourier transform will give the frequency to create the wave that create this harmonic. So this harmonic content of so we can use the harmonic to filter at using high pass filter, low pass filter, band pass or band stop filter, just like we do it before.
Actually, filter application is closely related to the Fourier transform that you might have learned before. Let's take this example of Fourier transform. Basically, this graph is amplitude against the omega, and omega is equal to 2 pi f as well. If you notice, the Fourier transform graph actually looks similar with the low pass impulse response. This graph, as I have mentioned before, Fourier transform converts the non-periodic continuous signal in time domain to continuous signal in frequency domain. And this graph actually is in discrete form. If I join all these points together to form the continuous signal in frequency domain, I will assume that all these graphs are derived from the Fourier transform. The band stop, band pass, high pass, and low pass as well. As the song that we have analyzed are consist of non-periodic continuous signal. Non-periodic, so we use Fourier transform to convert the non-periodic signal to continuous signal in frequency domain.
So now I'm gonna play back the original audio and the audio after the filter, so that you can hear it clearly. You can see you can hear the difference between the audio. So this is the original. original one, and this is the low pass. This is the high pass. The band stop pass filter. And lastly, this is the band stop filter. So, lastly, what I can conclude is after all of the fault filter, we can hear the output of the filter is different from each other, which is when it is low pass filter, it has maybe it has bass of the original audio, and the high pass filter, it will take the higher frequency of the audio, which is the treble. Okay, so I think that is all from me. Thank you.